expansions. Today we're taking you on an incredible journey back in time to explore the origins of our solar system. How did it all begin? What forces came together to create the sun, the planets, and all the celestial wonders we see today? Buckle up, because this is going to be an enlightening ride. About 4.6 billion years ago, in a quiet corner of the Milky Way galaxy, a giant cloud of gas and dust, known as the Solar Nebula, began to collapse. This collapse was likely triggered by a nearby supernova explosion, sending shockwaves through the nebula and causing it to contract under its own gravity. The Solar Nebula was vast, stretching across light years. As it collapsed, it began to spin, forming a flat, rotating disk with a hot, dense center. This center, called a protostar, would eventually become our Sun. The spinning motion caused by the collapse helped to flatten the nebula into a disk shape, which is why our solar system is more or less a flat plane. Within this spinning disk, regions of higher density began to form clumps, slowly pulling in more material through gravitational attraction. As these clumps grew denser, they also began to heat up, setting the stage for the birth of a new star. The temperature in the center of the protostar increased dramatically, eventually reaching about 10 million degrees Celsius. At these extreme temperatures, hydrogen atoms began to fuse together to form helium. This fusion process releases a tremendous amount of energy. Nuclear fusion is the process that powers the sun. It occurs when hydrogen atoms, the simplest and most abundant element in the universe, collide with such force that they merge to form helium atoms. This process releases a tremendous amount of energy in the form of light and heat. This energy counteracts the force of gravity, trying to collapse the star further, stabilizing the young sun and allowing it to shine brightly. As the sun continued to gather mass and heat up, it eventually reached a point where the pressure and temperature in its core were high enough to sustain nuclear fusion. This marked the birth of our sun, transforming it from a protostar into a main sequence star. The energy produced by nuclear fusion in the sun's core radiates outward, providing the heat and light that warms our planet and supports life as we know it. Surrounding the young sun was a disk of gas and dust. Within this disk, particles began to collide and stick together, forming larger and larger clumps. These clumps, known as planetesimals, were the building blocks of planets. As these planetesimals grew, their gravity began to attract more material, causing them to collide and merge with other planetesimals. This process of accretion led to the formation of protoplanets. The accretion process was chaotic. Countless collisions and interactions between particles and planetesimals occurred, leading to the gradual growth of larger bodies. Some of these planetesimals were shattered by impacts, while others merged to form increasingly massive protoplanets. Over time, the largest of these protoplanets cleared their orbits of smaller debris, becoming the dominant bodies in their regions of the solar system. Closer to the sun, where it was hotter, rocky planetesimals formed. These would become the terrestrial planets: Mercury, Venus, Earth, and Mars. These rocky bodies were composed of heavier elements like iron, silicon, and oxygen, which could withstand the higher temperatures near the sun. The process of differentiation played a crucial role in shaping the structure of these terrestrial planets. Differentiation is the process by which a planet separates into different layers, with heavier materials sinking to the core and lighter materials rising to the surface. In the case of Earth, this process resulted in a dense, metallic core made primarily of iron and nickel, surrounded by a mantle of silicate rock and a thin crust. This layered structure influences the planet's geology, including volcanic activity, plate tectonics, and the formation of mountains and ocean basins. Further from the sun, where it was cooler, icy and gaseous planetesimals formed, eventually becoming the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. The gas giants accumulated large amounts of hydrogen and helium, the lightest and most abundant elements. Their strong gravity allowed them to hold on to these light gases, forming massive, thick atmospheres. In the outer regions of the solar system, the ice giants Uranus and Neptune formed. These planets contain heavier elements and compounds like water, ammonia, and methane, which exist as ices in their cold environments. These icy giants also have thick atmospheres, but they are composed of heavier gases compared to the gas giants. The formation of these distant planets involved the accretion of icy planetesimals and the capture of gas from the surrounding nebula, leading to their unique compositions and characteristics. As the planets formed, the remaining gas and dust in the disk were gradually cleared away by the solar wind, a stream of charged particles emitted by the young sun. This process left the solar system mostly free of gas and dust, allowing the planets to settle into their current orbits. However, not all material was swept away. Some of it remained in the form of asteroids in the asteroid belt between Mars and Jupiter, and comets in the Kuiper belt and the distant Oort cloud. These remnants from the early solar system provide valuable clues about its formation and evolution. Asteroids are rocky bodies that never coalesced into planets, often due to the gravitational influence of nearby Jupiter. The asteroid belt is a region filled with these rocky remnants, ranging in size from tiny pebbles to dwarf planets like Ceres. Studying asteroids helps scientists understand the conditions and materials present in the early solar system. Comets, on the other hand, are icy bodies that originate from the outer regions of the solar system. The Kuiper belt, located beyond the orbit of Neptune, is home to many of these icy objects. Occasionally, gravitational interactions send comets hurtling toward the inner solar system, where they develop glowing comas and tails as their ices vaporize under the sun's heat. The distant Oort cloud is a theoretical shell of icy bodies that surrounds the solar system, serving as a reservoir for long-period comets that take thousands of years to complete an orbit around the sun. One of the key forces shaping the formation and evolution of the solar system is gravity. The gravitational pull of the sun held the solar nebula together and guided the formation of the planets. But gravity also played a crucial role in the interactions between planets and other celestial bodies. As the planets formed and settled into their orbits, their gravitational interactions created resonances. A resonance occurs when two orbiting bodies exert a regular, periodic gravitational influence on each other. These resonances can stabilize or destabilize orbits, affecting the distribution of material in the solar system. Jupiter's strong gravitational influence helped shape the asteroid belt. Jupiter's gravity prevented the material in this region from coalescing into a planet, leading to the formation of the asteroid belt instead. Resonances with Jupiter also created gaps in the asteroid belt, known as Kirkwood gaps, where the gravitational influence of the gas giant cleared out material. Similarly, the orbits of Neptune and Uranus are influenced by their mutual gravitational interactions. These resonances help maintain the stability of their orbits over long periods. The Kuiper belt also contains objects in resonant orbits with Neptune, such as Pluto, which is in a 3-2 resonance with the ice giant, meaning Pluto orbits the Sun twice for every 3 orbits of Neptune. In addition to planets, the solar system is home to a variety of other celestial bodies, including moons, dwarf planets, and rings. Many of these objects form through processes similar to those that created the planets. Moons, for example, formed from the disks of material that surrounded young planets. These circumplanetary disks were similar to the protoplanetary disk that surrounded the young sun. Within these disks, particles collided and stuck together, forming moonlets that eventually grew into moons. Some moons, like Earth's moon, are thought to have formed through giant impacts. According to the giant impact hypothesis, a Mars-sized body collided with the early Earth, ejecting a large amount of material into orbit. This material coalesced to form the moon. Other moons, such as the moon of Jupiter, likely formed in situ from the circumplanetary disk that surrounded the gas giant. These moons, Io, Europa, Ganymede, and Callisto, are some of the largest and most geologically diverse objects in the solar system. Dwarf planets are other fascinating objects in our solar system. These bodies are too small to clear their orbits of other debris, which is why they are classified as dwarf planets rather than full-fledged planets. Despite their small size, dwarf planets can have complex geologies and atmospheres, offering valuable insights into the diversity of celestial bodies in our solar system. Rings, found around all of the gas giants and some smaller bodies, are composed of countless small particles of ice and rock. The rings are thought to be remnants of moons or comets that were torn apart by the gravitational forces of their parent planets. And there you have it, the incredible story of how our solar system came to be. From a swirling cloud of gas and dust to the diverse and dynamic system of planets, moons, and other celestial bodies we know today. Don't forget to like, comment, and subscribe to Mind Expansions for more fascinating explorations into the mysteries of our universe.